So solving systems using elimination. So solving using substitution is convenient, and there's like a lot of times when it is the most efficient thing to do. And in fact, we will probably use substitution more often than not, mostly because most of the problems we encounter are in function notation, so it's easy to just set the functions equal to each other. So we don't have to worry about it getting messy. But there are some problems, like if we wanted to solve 2x plus 3y equals 9, and then 5x plus, oh, I don't want to do that one yet, I'm sorry. Equals that one. And then 6x minus 3y equals 9. So if we want to solve that system, we can see like none of the variables have a coefficient of 1, which is kind of what we looked for yesterday, right, when we were solving using substitution, because solving for a variable, if there's no coefficient, like no number in front of it, made it less messy, like we didn't end up with nasty fractions. Whereas this problem, regardless of which variable I choose and which equation I choose, no matter what, if I try to solve this using elimination or using substitution, I'm going to have to divide by something, and so I'll probably encounter fractions when I do my substitution. So we are going to use what's called elimination, which is just another way of getting to a point where we have an equation that has only one variable in it. And the idea of elimination is based on, it's actually based on substitution. It's just kind of hidden. So if I had the equation 2x equals 6, and I also have the equation x equals 3, let's pretend that those are separate equations and that they don't say exactly the same thing for a second. And so if I take the first equation, 2x equals 6, do you guys agree that it's totally cool if I add 3 to both sides of the equation? Can I do that? I mean, like, let's not worry too much on why the heck I would want to do that at this point, but it's valid, right? That's legal. I can add the same thing to both sides. So what if I, instead of that, I did that? Is that legal? It is, right? Because this statement tells me that x and 3 are the same. And so even though it looks like I added different things to both sides, I really added the same thing to both sides because x and 3 have the same value. So what that tells me is that we can add equations, meaning that you can add the left sides of an equation, and you can add the right sides of an equation, and you will get an equation that makes both true. And the reason that we're allowed to do that is that adding x to the left side is the same as adding 3 to the right side because x and 3 are equal to one another. So you've really added the same value to both sides of the first equation because of that equality in the second equation. And so we would never do any of that here because totally unnecessary when there's one variable. But when we have a system of equations and we're in a situation where we have two variables so we can't solve, if we add these two equations together, well, 2x plus 6x is 8x, and 3y plus negative 3y is just 0, and then 7 plus 9 is 16, and we've accomplished the same thing we did yesterday with substitution, which is to end up with an equation that only has one variable in it. And that happened because when we added our y's, we got 0. So, of course, 8x plus 0 is just 8x. So we have 8x equals 16, so x equals 2. Now in order to get y, you can use either one of the original equations. It doesn't matter which at all. So you just pick one. I'll use 2x plus 3y equals 7. So 2 times 2 plus 3y equals 7, which gives me 3y equals 3, so y equals 1. So my solution
Why is that not 1/3?
3 divided by 3?
Isn't it? Oh, never mind. I looked up.
Okay. So 2, 1. Does that make sense? Well, it's not always that nice. Like, we got lucky here because adding 3y and negative 3y gave us 0. And that's not always the case, right? You're not always going to get a 0 when you add initially. And if you don't get a 0 for one of your variables, then it doesn't do anything for you, this process, because the whole idea is that one of our variables gets eliminated. So sometimes we have to manipulate the equations so that we'll get that 0. Our goal when we do this is for one of the variables, and it doesn't matter which, you can just choose that one of our variables, the coefficients are opposite. So 5 and negative 5, or 10 and negative 10. So they have the same magnitude but opposite signs, so that when I add them, I'll get 0. So if we want to solve, say, 2x plus 3y equals 9, 5x plus 2y equals negative 5. So when I look at this, I think, okay, well, I can't really do substitution. I mean, I could, but it would get messy because I don't have any coefficients of 1. And so I'd like to do elimination. However, adding those two equations together doesn't eliminate either one of my variables. So we're going to manipulate these equations so that I have opposite coefficients on one of my variables. And it doesn't matter which variable it is. You guys get to pick. You want to get rid of x or y?
X.
Okay. So we're going to get rid of x, which means I need opposite coefficients on my two x's. So doing this is sort of like when you get common denominators, you just want to look at what the LCM is. So what's the LCM of 2 and 5?
10.
It's 10. So my goal is going to be to get a positive 10 coefficient for one of them and a negative 10 coefficient for the other. So I'm going to multiply both sides of this equation by 5. And make sure you do every single term, so you want to distribute that 5. So we have 10x plus 15y equals 45. And then I want the other coefficient to be negative 10, and so we're going to multiply both sides of this equation by negative 2. And notice I put that negative 2 in parentheses. That's important because if you write negative 5 and then you put that negative 2 like that, what did I just write? I wrote negative 5 minus 2, right? I wrote subtraction there when what we're really doing is multiplication. So even if you know in your head that you're multiplying, just be sure that what you write is what you intended, or means what you intended. So if you really didn't want to write the parentheses, you could do the dot, would be fine as well, but make sure it looks like multiplication. So we get negative 10x minus 4y equals positive 10. And now we can add those guys together, and 10x plus negative 10x is 0. 15y plus negative 4y is 11y, and 45 plus 10 is 55. And you'll note I always write that 0 because, like, instead of just like slashing those guys out. And the reason for that is that when we are in a situation where there's no solution or where there's an infinite number of solutions, both variables will add to 0. And if you get in the habit of just like slashing them out instead of writing a 0, you're going to end up with like people always say, like, there's nothing there, like, because your equation just is gone. And when we say there's nothing there, what we really mean is that that side of the equation added to 0. So in order to still have an equation, you need to write something there when you add it together. So this gives us 11y equals 5, so y is, or 55, so y is equal to 5. And then again, we can plug that back into either one of the original equations. And in fact, you can plug it into, so one of your original equations or one of the equations that you got after multiplying. In this case, there's no good reason for us to use the bigger numbers. However, that comes in pretty handy if the original equation has fractions in it and you clear fractions to get to those secondary equations. Then it's a little more convenient to plug back into an equation without fractions than to plug it into one of the ones with fractions. So it's just good to know you can use any of those preliminary equations to get x. So we'll just use the first one, 2x plus 3y equals 9. So 2x plus 3 times 5 equals 9. So 2x equals negative 6. So x equals negative 3. And so my solution is negative 3, 5. Any questions on the process? Okay, let's do another one. Let's do one with fractions. So let's say I want to solve, we will do 2/5 x plus 1/3 y equals, let's say 1/15. And then 2/3 x plus 1/2 y equals 1/3. So I like, when there's fractions like this, I like to kind of think of it in 2 steps. Like, I'm not going to worry about trying to eliminate a variable at first. At first, I'm just going to worry about getting rid of the fractions. So I'm going to clear fractions in both of my equations first, and then I can be like, okay, how can I eliminate a variable? So how can I get opposite coefficients? Sometimes it'll work out really nicely so that once you clear fractions, like, you don't have to do more work. But don't try to, like, get everything done at once because it can just get messy that way. So to clear fractions in my first equation, what do I have to multiply by? 15. So we'll multiply both sides of the first equation by 15. X plus 15 times 1/3 y equals 15 times 1/15. And then that gives me 6x plus 5y equals 1. So that's just my first equation. And then for my second equation, I have to multiply both sides by 6, yeah? So we'll do 6 times 2/3 x plus 6 times 1/2 y equals 6 times 1/3. Which gives me 4x plus 3y equals 2. So now we can worry about doing elimination, right? So my system now that I'm solving, like we can kind of like think of this as starting with a whole new system. I'm solving 6x plus 5y equals 1, 4x plus 3y equals 2. So it's kind of like just starting fresh with a whole new equation or a whole new system. We just don't happen to have fractions now. So I don't know, what do you guys want to eliminate? X or Y? X? Okay.
No, we're going to go Y.
What?
No, we can go with X.
Why are you changing your
I
mind?
don't know.
There's no right answer.
We'll just go with X.
I mean, well, I shouldn't say there's no right answer. Everything's a right answer. There's no wrong answer. X or Y work just as well. You want to go with X?
Yeah.
Okay, let's go with X. So if I look at 6 and 4, the LCM of 6 and 4 is 12. And so my goal is to get coefficients of 12 and negative 12 for my X's. So the first one, I'll multiply by 2 on both sides, which gives me 12x plus 10y equals 2. And then the second equation, I want my x to have a coefficient of negative 12. So I'm going to multiply both sides by negative 3. Which gives me negative 12x minus 9y equals negative 6. And then we'll add 12x plus negative 12x is 0. 10y plus negative 9y is 1y. And then 2 plus negative 6 is negative 4. Well, that worked out nicely. So y is just equal to negative 4. So now I want to plug that back in to one of my equations. I'm not going to use either of these because those are ugly and they don't look like fun. So instead, I am going to just use one of these secondary equations. They're equivalent to the original equations, so they'll do the same trick. I just don't have to deal with all the fractions. So we'll just pick 6x plus 5y equals 1. So we have 6x plus 5 times negative 4 equals 1, which gives me 6x equals 21. So x equals 21/6, also known as 7/2. And my solution is 7/2 negative 4. Okay, I'm going to have you guys try one. Anybody still writing? Good? Okay. Let's solve (3x minus 4y equals 1 and 5x plus 3y equals 21. Because it doesn't matter which one you do, like you get the same answer no matter what. And it's also true that you get the same answer regardless of if you use elimination or substitution. So if you wanted to spend way more time on this problem and mess with a bunch of messy fractions, you could do substitution and you'd get the same answer. Because the solution, if you think about like the graphs we did yesterday, if I graph these two lines, there's a solution, and that solution exists regardless of how I choose to find it. So it doesn't matter, like there's no wrong choice as far as which variable to eliminate or which method to use. It's just that sometimes one choice is easier than the other. So I'm going to eliminate my y's. When I look at that 4 and the 3, I want to make the coefficients of y 12. And so I'm going to multiply by 3 on both sides of the first equation, which will give me 9x minus 12y equals 3. And then I'm going to multiply by 4 on both sides of this equation. Now notice that I already had opposite signs, like one of my coefficients was already negative, so that's why I'm not doing like a negative 4. Like if you eliminated the x's, one of your numbers that you had to multiply by was negative, but that was only because they both started out as positive. So this would give me 20x plus 12y equals 84. So adding gives me, that's a horrible straight line, adding gives me 29x plus 0 equals 87. And so x equals 3. Yeah? And then if I plug that back in, I get y equals 2. Does anybody want to see me do that? Because I think you guys all did it on your own and got it. Yeah? Okay, so we're going to move on a little bit to some applications, but we'll get to practice this because we're going to solve applications using systems, so we'll still get to use our methods for solving systems as we do our applications. So when we first did application problems, like back on like the second day of class, we often had problems where there were two unknowns, but one of these unknowns was stated so clearly in terms of the other that we didn't really need two variables, right? Like we'd be like, the length is 5 more than the width, and so it was really easy to call the width x and the length x plus 5 because that relationship between the two was so clearly stated, like how to get one from the other. So that's not always the case. Sometimes we have applications where there's two unknowns and we're given relationships between them, but the relationships aren't clear enough to like write one in terms of the other right away. And so that's when it's a good idea to use two variables instead of just the one. So for example, we can solve, let's say the difference of two numbers is 3, and then 2 times the smaller number plus 3 times the larger number. is 39. And we want to find the numbers. So here I'm given relationships between these two numbers, but the relationship isn't explicit enough that I really want to write one in terms of the other. So like it doesn't tell me how to find the second number from the first, or that it's like they're consecutive, so I can just add one or something like that. So I'm going to start the same way I do with any other application. I'm just going to list my unknowns. So in this case, we have the smaller number and the larger number. And I'm going to call the smaller number x, and then I'm going to call the larger number y. So it's totally up to you when you're solving an application whether or not you use, or whether you use one variable or two variables, and you get to make that choice just depending on the problem. The key is if you choose to use two variables, then you have to write two equations. So the only way for us to solve for two separate variables is if we have a system of equations. So we have to look for two pieces of information in the problem that are separate and will give us two separate equations. So which we have here because we have kind of two sentences. Let's look at the first one first. It says the difference of two numbers is 3. So what equation would that give me?
X minus y.
Okay, so x minus y equals 3. Does everybody like that equation exactly as it's written?
Oh, larger minus.
Yeah, so we said that x is the smaller number, and so if we did a smaller number minus a bigger number, that would always give us a negative, right? And 3 is positive, so it has to be the larger minus the smaller. And sometimes like that doesn't matter. You'll just, when you solve, you would end up with like x being the larger and y being the smaller if you got that order messed up. However, in this particular problem, because the other sentence is written in terms of smaller and larger, if I get those switched here, but then use them as I've written them originally, then I'm not actually translating the equation correctly. So you want to be careful that's why I labeled them like smaller and larger instead of just like first and second, like so I'm really clear about which one is bigger. So we want to write this equation as, whenever you have a difference, you always want to do the bigger number minus the smaller number to get a positive difference. And then that second sentence can be translated like pretty literally word for word into an equation, right? Like 2 times is 2 times. The smaller number we called x, plus is plus 3 times. And then the larger number we called y. The word is always equals, and then 39. So like really just straight through translate it into 2 times x plus 3 times y is equal to 39. So now we have a system, and then we get to decide if we want to solve it by substitution or elimination. What do you guys want to do? Substitution? Okay. I like substitution on this one too because we have coefficients of 1, so it's pretty simple to solve that first equation for y. So this is y equals x plus 3. So I have 2x plus 3 times x plus 3 equals 39. So 2x plus 3x plus 9 equals 39. So 5x equals 30, and x equals 6. And then we'll plug back into the other equation. We get y equals 6 plus 3, which is 9. And on these problems, when we do applications, we don't need ordered pairs because it's not actually asking for a point on a graph. We want to answer the question, like, what are the numbers? So you'll just write a sentence rather than writing an ordered pair like we do when we're just solving these algebraically. So the numbers are 6 and 9. Good? Questions? Okay, let's do another one. Let's do basketball. So let's say the Trailblazers scored 60 points on a combination of 2-point shots and 3-point shots. If they made a total of 27 shots how many of each kind of shot did they make? Okay, so again, we're going to just identify our unknowns. In this case, we want to know how many of each shot. So the number of 2-point shots and the number of 3-point shots. Which we'll call X and Y. And then a lot of these problems, there's more numbers in these than like some of the problems we've done in the past because we have to have two separate relationships, right, for our two separate equations. So I usually think of the two different types of equations. So one of my equations has to do with like quantity, and one has to do with value. So quantity of baskets that they make, and then the value of those baskets in points in this case. If it's a problem that has to do with money, my value equation might be like in dollars. And that's why like when I wrote what my unknowns are, I was pretty specific as far as it being like the number of 2-point shots, because that tells me that X and Y are like a quantity of shots. They're not it's not like points or dollars or whatever. So I'm really clear about which is which. So that means that in my quantity equation, I'm just adding the number of baskets, right? So X plus Y. And how many shots did they make?
27.
Right, they made a total of 27 shots. And then for my value equation, I'm talking about how many points were scored. So I have to think about, like, if I make X 2-point shots, like how many points that gets me. Well, I get 2 points per shot, so I'll multiply that by the number of that type of shot. And so that's how many points I get off of my 2-point shots. And then 3y is the number of points I get off my 3-point shots, and that has to total my 60 points. And one thing that can help when you're like, just to make sure that you're putting all the numbers in the right place, is if you think about units. So this number, and this number should all have the same units, right? So 2 points, 3 points, 60 points. So that helps make sure that I've put, the mistake that sometimes happens is like the 27 and 60 gets mixed up. So if you think about your units, that'll really help. And in some of the money problems, like I think you guys have some like quarter and dime problems tonight, be sure that it's all in dollars or it's all in cents, right? So like if your total amount of money was like $55, you can't use 25 as the value of a quarter because that's 25 cents, right? You'd have to either change your $55 into cents or write your 25 cents as $0.25. So just make sure your units match on these. You guys want to use elimination or substitution? Substitution. Okay, go for it. In fact, if you thought you want to use elimination, you guys can use different things. So we would have like y equals 27 minus x. So 2x plus 3 times 27 minus x equals 60. If I skip some steps to save time, we get negative x equals 81, negative 21. So x equals 21. And then y equals 6. I skipped a bit just to, because we don't have a lot of time, but is that good? And then 21 2-pointers and 6 3-pointers. That's my sentence, and we're all set.